So this is going to start chapter 17, which is all about electrochemistry. We're going to start off with a little bit of a review because we did cover redox reactions in chapter 4 in fall semester. And so we're going to start off talking about redox chemistry, which falls underneath the umbrella of what's called electrochemistry. And so this is a branch of chemistry that deals with the interconversion of electrical energy and chemical energy. So, batteries. So some of the key ideas, if you don't remember from chapter 4, we had reduction, which was gain of electrons. We had oxidation, which was the opposite, the loss of electrons. And so you may remember oil rig. Another thing is that electrons are conserved. This was a law we talked about, but it means that the electrons transferred from one to the other must be conserved. So electrons are not lost in the process. And then we have what was called the oxidizing agent. And this was the species that was being reduced. And the reducing agent is the opposite, the one being oxidized. Okay, because the oxidizing agent is doing the oxidation. Now, I don't know, I guess. Okay, there it is. My things got changed around a little bit. Okay, so now we're going to talk about a certain type of cell, which is called a galvanic cell. Okay, these are, it's an experimental apparatus used to generate electricity. So this is the electrochem lab. That's what we were setting up, is a bunch of these galvanic cells. An example of the cell is below. So there's a couple of important things to note here. One is that you're going to have an area of the battery or the system which is called an anode. The anode is where oxidation occurs. Okay, so this is where electrons are lost. And then you're going to have what's called the cathode, where reduction occurs. And then electrons are going to travel from left to right because they're lost on the left and gained on the right. So it matches our definition. Now the electrons are being transferred via this thing, these wires right here. But which is this one right here, allows for the electron transfer. However, in order to complete the circuit, there has to be a balance, and that balance is called the salt bridge, and this is where the ions are provided to keep the charges balanced. So in the video you're going to see that he uses a piece of chromatography paper as the bridge. In our lab we would have used a piece of string, but they both do the same thing, which is to bridge the two solutions together and to balance out the charges by providing ions. Alright, so at each electrode, we're going to write the half-cell reactions that are occurring. So on the anode portion, we have zinc solid undergoing oxidation to make zinc 2+ and 2 electrons. So that's right here. Okay, that's the half cell. The other half cell must be copper gaining those 2 electrons. To form copper solid. Okay. Now there's another way we could write this to represent the cell, and that's called a cell diagram. Okay, so it's just a description of, if we say we don't have a picture like we do right here where we can see what's going on, we have what's called the cell diagram, which allows us to write it out. And then there's a couple of important things. You're always going to write the anode reaction, cathode reaction. So it's in the direction of the electrons flowing. So you're going to pretty much write the picture left going to right. The vertical bars like right here, represent phase boundaries. So this is solid to liquid to gas to aqueous, any type of transition like that. And the double vertical bar, this one right here, represents the salt bridge. Okay, so it's going to separate the anode and the cathode. Basically what's separating our beaker. Okay. All right. The concentrations of all ions or pressures of gases are typically included when they're not standard conditions like 1 molar or 1 atm, but you're not always given the concentrations, so we usually don't worry so much about writing them unless they're atypical values. So let's practice writing the cell diagram, and this is also sometimes called cell line notation. It just depends on the preference of the author of the textbook, which one they use. So we're going to start with the anode. Well, in this case, my anode is the zinc solid. And it's forming zinc 2+. So I'm going to use this solid one line to represent the phase diagram of solid to aqueous because they're different phases. And then I'm going to use 2 lines to separate my anode from my cathode. And then it's going to be cathode reaction and my cathode, because the anode and the cathode are going to be these solid pieces right here. Okay, the solid pieces. So in this case you can see zinc anode, copper anode, zinc solution, copper solution. Now the reason why the sulfate isn't in there is because it's a spectator. Okay, so no spectator ions show up. Okay, so you need to be able to do this, okay, to describe a cell like this, because this is what your quiz 10 is going to be over. Okay. All right, so reduction potentials. When the voltage of the galvanic cell shown above is measured, it's seen to be 1.1 volts. And this is going to be predicted using what are called electrode potentials, and we see tables of them down here. There are tables upon tables of reduction potentials for all the possibilities, but one thing that they have in common is all the values are compared to a standard reference electrode called the standard and hydrogen electrode, or SHE for standard hydrogen electrode, which we arbitrarily set to exactly 0.00 volts. So it makes a really good reference because it's 0. Now the thing about these tables is they're all written with respect to reduction, meaning you're not going to see an oxidation half reaction. The standard reduction potential is the voltage associated with the reduction reaction at an electrode where we're at standard conditions. Now, in order to calculate the potential of the cell, which is the one we're seeing right here, the 1.1 volts, we have this equation right here, which is E cell naught equals E naught of the cathode minus E naught of the anode. So you have to be able to define who's the cathode, who's the anode, and then you're going to subtract them. Now, although the anode is actually being oxidized, the minus sign in this formula takes into account that the reverse reaction is happening. Therefore, we can just use the values straight out of the table. So we had this anode reaction and this cathode reaction. Okay, I'm going to leave that off just because I didn't do it on the other one. So I'm going to look up the E naught for the anode. So zinc negative 0.76 volts. So I'm going to write it just as it is straight off the paper. And then copper, I wish these were in alphabetical order, is positive 0.34. Okay, so now that I've identified my cathode and my anode, which they were already given to me, which is kind of nice, I'm going to plug in my values. Subtract the negative number. And when I add them up, I'm going to get a oh, that's not right. I have the wrong numbers written on my paper. Oh, lo and behold, it should equal that value. I wrote down this one on my paper, and that is not the right reaction, so whoopsie. Okay, so that's how you calculate the standard potential of the cell. Okay, so you do not need to memorize these, but what you do need to know is you need to know how to interpret these: anode on the left, cathode on the right, salt bridge, wire. You need to be able to write the half cell reactions that are occurring, write them in cell line notation with the cell diagram, and then calculate the E cell naught for the ones that you're given. Okay? So not too difficult. So a few rules to keep in mind when you're using the table above: the more positive the E value is, so like up here these are very positive values, the greater the tendency of the substance is to be reduced, so to gain electrons. Okay? Meaning the more negative it is, these tend to be more oxidized. Okay? The half cell reactions are reversible. Depending on the conditions, any electrode can act as an anode or cathode. It just depends on which two electrodes are coupled. And so we see that in the lab that we're going to do this week. Under the standard state conditions, any species on the left of a reaction will spontaneously react with a species that appears on the right, located below it on the table. And this is sometimes called the diagonal rule. So, like on the left and on the right. On the left and on the right. Okay? I hope that makes sense. And it's diagonal because it's at a diagonal. Changing the stoichiometric coefficients of the half cell reaction does not affect the E naught value. So meaning if I took all of these and multiplied them by a factor of 2, this does not multiply by a factor of 2. Okay? It's a constant amount. Does not matter on the stoichiometric coefficient. And like delta H, delta G, delta S, the sign of E naught changes, but its magnitude remains the same when we reverse a reaction. So say, for example, that I took this cell up here and I wanted to make copper my anode and zinc my cathode. Well, in this case, the E cell naught value would be minus 1.10 volts. So it reverses the sign, but it keeps the same magnitude, just like delta H, delta S, delta G. Okay? So you might see we're going somewhere with the relationship between all of these. Okay? So relatively short video on the redox chemistry, but make sure you study. This particular lesson is going to be your quiz 10, kind of a practice quiz, because some of the stuff is just refresher, and so hopefully it should be a pretty straightforward quiz.